Hey there. This is the lecture for section 8.1a, the law of sines. There's three sections for 8.1. In the first part here is the law of sines, and the second part, 8.1b, will be the law of cosines. And then there's a third part, 8.1c, that addresses applications using the law of sines and the law of cosines. All right. So what is the law of sines? The law of sines is used to find angle measures or side lengths of a triangle that does not have a 90-degree angle in it. So the law of sines is for non-right triangles. If we have a right triangle, of course, we can use the definitions for the trig functions. The sine definition being the opposite over the hypotenuse, the cosine definition being the adjacent over the hypotenuse, and the tangent being the opposite side over the adjacent side. All right. These trig functions do not apply, though, to non-right triangles. All right. So the two tools that we can use to solve non-right triangles are the law of sines and the law of cosines. All right, the law of sines is stated here. It's simply a set of ratios that are equivalent, right? So if we have a triangle and we label the angles alpha, beta, and gamma, right? And then the side across from alpha is side A, the side across from beta is side B, the side across from gamma is side C, then the law of sines says that the sine of alpha over A is equal to the sine of beta over B. It's also equal to the sine of gamma over C. This ratio of an angle measure to its opposite side is always going to be the same. All right, so let's look at an example using the law of sines. All right, if we know two angles and one side of a triangle, using the law of sines is really straightforward, right? So we refer to these triangles where two angles are known as an angle side triangle. That's this one here, angle side. So we would consider this an angle side triangle. This example over here has angle side angle. So we might call that an ASA triangle. All right. Now, it says straightforward case because when we have angle side or angle side angle, the law of sines is excuse me. The law of sines is not tricky at all. However, if we don't have two angles and one known side, it can be a little challenging. Let's look at the straightforward case first, though. All right, so if we label our triangles, let's make the lower left angle. Let's always make that one alpha, and then we'll go around the triangle counterclockwise. So the next angle would be beta, and gamma would be up there. All right, so side A is across from alpha. That'll be that side. B is across from beta. We know the length of B is 18. C is across from gamma, so that one will go there. All right, so there's only going to be one ratio that has both a known angle and a known side. So we start with that, and in this triangle it's beta and B. So we'll say the sine of beta, 110, over 18 is going to be equal to, and what else do we know? Just one other angle measure, so we've got to do alpha and A next. So that'd be equal to the sine of alpha, which is 40 degrees over A. All right, we can use cross products to solve this equation. So we'll get A times the sine of 110 equal to 18 times the sine of 40, and then divide both sides by the sine of 110. Divides out here, and we can determine the length of side A. All right, so that's going to be 18 times the sine of 40. Let's see if I can wake my calculator up. There it is. Yeah, we don't want to graph that. All right, these are degrees. I better check my mode, make sure I'm in degree mode. I am in degree mode. Okay, that's good. So then I'm going to say that A is equal to 18 times the sine of 40 divided by the sine of 110. All right, and that value is approximately 12.3. Okay, so there's side A, 12.3. All right, so now we now got to try to figure out, whoops, we need gamma and we need C. Now I know neither one of them, so I can't use a ratio here, but I do know that the sum of the interior angles of a triangle equal 180, right? So I can say that gamma is equal to 180 minus 110 minus 40, or gamma is going to be equal to 30 degrees. Okay, so now I do know that angle, and now I can set up a ratio and solve for C. All right, so I can say the sine of 110 over 18, that's alpha over A, I'm sorry, that's beta over B, is equal to the sine of 30, that's sine of gamma, over C, and I can solve for C. Okay, with cross products and dividing, you can see that C is equal to 18 times the sine of 30 divided by the sine of 110. And that value is about 9.6. All right, so C then is about 9.6. Does that make sense? Well, in a triangle, the smallest angle should have the smallest side across from it. Smallest angle is gamma at 30. Smallest side is C at 9.6. The next smallest angle should have the next smallest side, 40 with 12.3. The largest angle should have the largest side, 110 with 18. So that does make sense. All right. So that's an angle-side triangle. With an angle-side-angle triangle, there's really nothing much different. We're just going to do ratios the same way. We just need to decide what our alpha, beta, and gamma are and then label our sides. We'll just say this guy is alpha. This angle down here is beta. And we'll put gamma up there, which means C is across from that. A is 15, and B is going to be across from beta. All right, using the law of sines again, my known angle and opposite side is not here. So I'm going to have to find, before I use the law of sines, I'm going to need to find this third angle, right? Because I don't have a ratio I can set up. I've got angle beta, but I don't know B. I've got angle gamma, but I don't know C. But I can find angle alpha. It's 180 minus 75 minus 45. So what is that, 50? Let's see, 75 and 45. Yeah, 60, sorry. It's 60 degrees. So now I can set up a ratio with alpha, sine of alpha and A. So I can say the sine of 60 over 15 is equal to, and it doesn't matter which angle I saw, or which side I solve for next, so I guess I'll just do beta, or I'll do B, sorry. So it's equal to the sine of beta, or the sine of 75 degrees over B. Solving for B with cross products, B is going to be 15 times the sine of 75 divided by the sine of 60, which is sine of 60. There it is, 16.7 approximately. All right, and then lastly, we have one more side here. I sometimes have students say, well, can we use the Pythagorean theorem? And the answer is no, you cannot, because it's not a right triangle. The Pythagorean theorem only applies to right triangles, so we can't use it. We've got to use the ratio of law of sines to find C, right? So let's see, we'll use alpha and A again. So we'll say the sine of 60 over 15 is equal to sine of gamma, that's 45, over C. Solving for C, we see that C is equal to 15 times the sine of 45 divided by the sine of 60, which is sine 60. There it is. About 12.2. Okay. Now always do some common sense to make sure you calculated these properly. Do they make sense? Well, the largest angle has the largest side, next smallest medium side, and smallest has smallest side. So I'm satisfied with those answers. All right, so the law of sines is pretty straightforward. This is on your formula sheet. It's right at, where is it? Down at the bottom left-hand corner of your formula sheet. Okay, but it can get a little bit tricky, right? It can get a little bit tricky, and we call this the ambiguous case for the law of sines. So if you look at some given, let's see if we can maybe sketch. Let's see if we can maybe sketch that triangle that's being described there with alpha, A, and beta. All right, so let's see, what might that look like? Alpha, about 43.1 degrees. So I'm going to try to do it a little bit to scale. All right, so this is going to be my alpha. It's going to be my 43.1 degrees. Okay, A across from it is 184. Beta is going to be over here, right? But B is much bigger than beta. So B across from here has to be the largest side. All right, so maybe we got to do it something like that. All right, we know A, it's 184.2, right? This is beta over here. This is gamma up there. This is, nope, sorry, this is C. Up there is B. And we know B. B is 242.8, okay? All right, so that's sort of a sketch of one triangle that satisfies these given conditions. However, I can't change this angle here, but I don't know what angle beta is, do I? So I could potentially take this leg, swing it around like this. All right, look at this. Make this acute angle over here, beta, right? And it's still, see the dotted triangle, that all three angle acute triangle, it still meets these same conditions that are given here. So this is what we call the ambiguous case for the law of sines, or it's the ambiguous triangle. There are two triangles that can be formed with those given conditions. All right. Well, drawing these sketches can be a little bit challenging. Do I really need to do that? No, I don't. If I want to solve a triangle that might be ambiguous case, I don't need to worry about it when I start. When I start, I can just go ahead and set up ratios and see what values I find. Okay, so if I look at what we have here, I know alpha and A, so that's one ratio that I want to use. So I could say that the sine of alpha, 43.1 over A, 184.2, is equal to the sine of beta. It could be any one of these two angles, right? Sine of beta, I'm going to find what it is though, over B, which is 242.8. Okay, that's a legitimate ratio. I'll just use cross products to solve. All right, and I'll have the sine of beta being equal to 242.8 times the sine of 43.1 divided by 184.2. All right. So if I calculate that, that's going to be the sine of beta. So if I want to know beta, I just do inverse sine of both sides, right? So beta then is going to be the inverse sine of the expression there for the sine of beta. 242.8 times the sine of 43.1 over 184.2. Right, so let's just put that in the calculator and see what that is. We'll put the calculator over there. All right, so 242.8 times the sine of 43.1. Close off that. Okay, divided by 184.2. So it looks like beta, am I in radians? Did I somehow get mode switched to radians? No, that's degrees. Oh, that doesn't look right to me. Let's see what I did wrong here. I typed something in, 242.8 times the sine of 43.1 divided by, let's see, did I do my cross products wrong? Let's try that again. Oh, I forgot to do inverse sine, that's why. All right, so I want to find the inverse sine. Now I could just do inverse sine of answer, and that's going to get it to me, so I think I'll just do that. There, inverse sine of answer. And there it is, 64, about 64 degrees. We'll say 64.2 degrees. All right, so beta, so which angle did I find? Did I find this obtuse angle or the acute? I found the acute angle. I did. And that's fine. It doesn't really matter which one I find, right? Here's, in fact, let's draw, I've got two triangles. Let's draw the second triangle. How should I do this? The second triangle, I'm just going to make it a whole separate triangle in red. All right. So it's going to have alpha, which was given, 43.1, and it's going to have beta sub 1, right? Beta sub 1, that's the first beta that we found, and we just found that to be 64.2 degrees. And there's gamma that I have to find yet. All right, and then let's see, we've got given is A, so let's put that over here, 184.2, and given, we've got B given, 242.8. We don't know what C is yet. Okay. So how do I find gamma? Well, I subtract from 180, right? So gamma, and this is gamma sub 1, because look, there's going to be two angles, a different angle over here. It's going to be bigger, right? So we're doing gamma sub 1 here. This guy over here was beta sub 1. Gamma sub 1 is 180 minus 43.1 minus 64.2. Let's see, 43.1 minus 64.2, 72.7. All right, so there's beta sub 1 and gamma sub 1. So that's the first triangle. But there's another triangle that we can solve over here. There's another triangle that's going to have beta sub 2 in it, right? This guy over here was beta sub 1, and this one's got, it's going to have a gamma sub 2, which is going to be this larger angle. So the question remains then, how do we go about finding the second beta, right? Well, look at this. These two angles, aren't they supplementary angles? Can we do that? Can we say that? Can we say that beta sub 2, well, now that I'm into my colors, I want to do it this way. Can we say that beta sub 2 is 180 minus beta sub 1? Yeah, sure, why not? All right, let's see, 180 minus, what is beta sub 1 again? It was 64.2, right? So what is that? Calculator, 180 minus 64.2. Oops, didn't do that right. Let's try that again. 180 minus 64 point, there it is, 2. All right, so that's 115.8. 115.8 is going to be my beta sub 2 right here. All right, so then now what? Well, I've got to find my gamma sub 2, right? Well, I know that these are going to add up to 180, so I can say gamma, oops, not lambda, gamma sub 2 is 180 minus 43.1, this guy, minus beta sub 2 that I just found, 115.8. All right, 43.1 minus 115.8, and there it is, it's 21.1. Okay, so that's my gamma sub 2, this one right here, 21.1. In fact, I didn't draw that right. The big purple, that shouldn't be that. That should be this. There we go. All right, makes sense? So there's two possible triangles. Now, what if you're not real good at drawing triangles to scale? No worries there. You don't have to. There's a little rule that you can follow. All right, to find out if some conditions result in an ambiguous triangle, first just use the law of sines to find the unknown angle. All right, to find the unknown angle. Once you find it, subtract it from 180. This will be a second possible angle. All right, so you'll assume that two triangles are possible. Now what you're going to do though is add that second possible angle to the given angle. All right, if this sum is less than 180, then there is a second triangle possible, and it is an ambiguous triangle, right? If you add this angle that you found to the given angle and it's greater than 180, then no, there is not a second triangle. It's going to be 1. All right, so that's sort of a procedure that you can follow to determine if you are dealing with a second triangle or not. And all triangles where you've got two sides and an angle that's not in between those two sides, right? A side-side angle triangle. All those types of triangles are called ambiguous triangles because there's always going to be a possible second triangle that you have to test for. All right. So let's just go through just one more time. Let's go through some more examples. All right. Let's look at this one here. Let's look at these conditions here and see if this results in an ambiguous triangle. All right. Now I like to sketch. I like to know, and what am I looking at here? Side A is 105, B is 45. It's smaller. Side B is 50. All right. So if I'm sketching this guy, I think 50 degrees is maybe about that. I do it a little bit to scale. Across from that is 45. Alpha is going to be over here. So this side over here has to be really long. In fact, let me do this lower. I want to make this a little bigger so I can write better. All right, so this side over here has to be really long. We'll say that's 50 degrees. It's beta. Alpha is going to be here. It's got the longest side. So there's alpha. Up here is our gamma. There's A. B we know is 45. And then C would be down here. All right, so there's kind of a sketch of what this might look like. Now let's just, we know that it's a possible, we know that it's an ambiguous triangle because I'm given, oops, I missed one of my angles. B was 45. No, what did I miss? A is 105. There we go. because I'm given two sides and an angle, and it's not the enclosed angle, right? It's a side-side angle triangle. Since this is a side-side angle triangle, I know that it's ambiguous, and there's a possible second triangle. All right. I'm not going to worry about it, though. I'm just going to set up some ratios and use the law of sines. All right, so I know beta and b, so I definitely want that to be part of my ratio. I want to say the sine of beta, sine of 50 over b, 45, is equal to the sine of alpha, which I don't know, over a, which I do know, 105. All right, using cross products and inverse sine, I can now say that alpha is going to be the inverse sine of 105 times the sine of 50 over 45. Right? And let's see what that is for angle alpha. All right, inverse sine of 105 times the sine of 50 divided by 45. Oh, so what does that mean? Error. I've got a domain error here. A domain error. Let's see. What could that mean? Let's look at our equation again. I don't see a problem. Looks like I got that typed in. Let's see what the argument is for this inverse sine here. Let's clear it. All right, so let's see what 105 times the sine of 50 divided by 45 is. Oops, divided by 45. Let's try that again. My 4 didn't click. There we go. 1.787. Can I have any angle that has a sine of 1.787? No. No. So that's why we have a domain error. Well, what does that mean in the context of our triangle here? Well, it means this. It's an impossible triangle. This length of 45, this is a short leg. 45 only goes that far. Something like that. So it doesn't ever meet up. Since my calculator told me domain error, I know that I have an impossible triangle. Okay. All right. Let's look at one more. Okay, here we have alpha at 119 degrees. Okay, that's an obtuse angle. Let's see, an A is 26. Let's see if we can draw this guy. We're going to say that's about 119 degrees. That's our alpha. Okay, B will be over here. So our beta, our gamma, our C, our A, which is given as 119, and our B, which is given as 14. There's my triangle. All right. I'm noting this is a side-side angle triangle, right? When I note that it's a side-side angle triangle, I know that it's it's an ambiguous triangle, right? So there's possibly two triangles, keeping that in mind. All right, let's just set up the first ratio and solve. The sine of alpha, that's the sine of 119 over A, 26. B is, so let's try to find beta first. All right, so that's going to be equal to the sine of beta over 14. All right, so with cross products, I'm solving for sine of beta and then inverse sine of both sides for beta. We can see that beta is going to be the inverse sine of 14 times the sine of 119 over 26. All right, let's see what that is. Inverse sine of 14 times the sine of 119. Oops, another one there. Okay, 119 divided by 26. Looks like it's about 28 degrees. All right, so there's that guy, 28. Now I can find I can find, so beta sub 1. Is there going to be a beta sub 2, though? Is there going to be a beta sub 2? We'll go back to our rule. Let's see what it says. I found that unknown angle. Now I have to subtract it from 180. Okay, let's do that. What is that? Subtracted from 180. So here's my unknown angle. It's 28 degrees. So 180 minus 28 is 152. All right. So I subtract that found angle from 180. And that's my second possible angle. I'm going to add that to the given angle to see if it can make a triangle. All right. So 152 is a possible second angle for beta. Right? It's a possible second angle for beta. Is it though? Let's see. Add 152 to the given angle? Oh, no way. When I add the given angle, I'm way over. That's way over 170 or 180 degrees. Sorry. So here, I know that there's no second triangle. It's not possible. And that's usually going to be the case when you have an obtuse angle. When an obtuse angle is given. All right, so since there's no second triangle, I don't have to worry about beta sub 1, beta sub 2. I just need to find gamma and C. Gamma is 180 minus 119 minus 28. All right, that's 33 degrees, so that's this guy, 33. C, then I have to use a ratio. Let's see, we'll use alpha and A again. So we say the sine of 119 over 26 equals, sine of 119 over 26 equals, let's see, we need gamma, the sine of 33 over C. Right? Solving for C, C is going to be 26 times the sine of 33 divided by the sine of 119, which is 26. Where did I get 26 from? What did I do wrong here? I'm doing something weird. Oh, I didn't write that. A is supposed to be 26, not 119. All right, so that's right. So 26 times the sine of 33. Oh, my software is tired. Divided by the sine of 119. And there we have it, about 16.2. Okay, makes sense. 33 with 16.2, 28 with 14, yeah. All right, so there's the third situation where there is only one triangle. There is only one triangle. All right, now look at these triangles here. This is interesting. Look what we have here, side, angle, side. So we have a side, angle, side triangle. And here we don't know any of the angles. We only know side, side, side. All right. Could we use the law of sides to solve these two triangles? On the one with no angles given, clearly no. Because how could I set up a ratio involving an angle measure when I have no angle measures, right? How about here? I have one angle measure. I don't know the side across from it, though. And because I only have the one angle measure, I don't know how to find out what the other two are. So I can't set up ratios here either. So the law of sines falls on its face here. It does not work in solving side, angle, side, and side, side triangles. Those types of triangles require the law of cosines. All right, so that's going to end the lecture for 8.1a. 8.1b coming up next.